Section 5.2, Power Functions and Polynomial Functions. In this section, you're going to identify power functions, identify end behavior of power functions, identify polynomial functions, identify the degree and leading coefficient of polynomial functions. Identifying power functions. A power function is a function with a single term that is the product of a real number, a coefficient, and a variable raised to a fixed real number. Here are some examples. F of x equals x squared has a coefficient of 1, the variable is x, and the power is 2. G of x equals x to the third is another power function. The coefficient is 1, the base or the variable is x, and the power is 3. H of x is also a power function. There is a coefficient 1, the variable is x, and the power is 6. Identifying end behavior of power functions. So we have 4 behaviors for the power function depending on the power, if it's even or odd, and depending on the constant k or the coefficient of the function. So if we have the power function f of x equals to kx to the n power, that is in general the equation for any power function. So when k is positive, we have 2 behaviors to identify. The first behavior is when the power is even. When the power is even, the behavior of the function is going to look something like this. The behavior of the function is going to look like that. What we care about is the end behavior, which is this side and that side of the behavior. We don't care what happens here in the middle. And we can describe the end of the behavior of the end function like so. We say when x goes to negative infinity, in other words, on the left side of x axis, f of x goes to infinity. So on the left side of the x-axis, the function goes up, which goes to positive infinity. And then on the right side of x, or when x goes to positive infinity, notice how the behavior of the function, it goes to positive infinity as well. So this is how we're going to write the end behavior of that function. If the power is odd, then the behavior of the function is going to look like this. So again, what we're going to focus on is the end behavior, and we don't care what happens in the middle. Again, on the left side of x, or when x goes to negative infinity, so on the left side of x, the function goes down, which means f of x goes to negative infinity. And then on the positive side of x, the function goes up, so f of x goes to positive infinity. Here is another case. If k is negative, when k is negative, we notice that if the power is even, if we have an even power, then the graph of the function is going to look something like this, which means on the left side of x, the graph goes down. So when x goes to negative infinity, f of x goes to negative infinity as well. And then on the right side of x, the graph goes down, which is when x goes to positive infinity, that is the right side of x, f of x goes down or goes to negative infinity. When the power is, so this is even, the power is even. When the power is odd and k is negative, you notice this behavior of the function. So on the right side of x, or when on the left side of x, or when x goes to negative infinity, the graph of the function goes up, or f of x goes to positive infinity. And then on the right side of x, the graph goes down. In other words, we're going to say when x goes to positive infinity, f of x goes to negative infinity. So that is how we're going to identify these end behavior of the function depending on the leading coefficient, or k, and the power of that power function. If it's even, both arms of the function are going to go in the same direction. If it's odd, one arm up and one arm down. And again, you have to memorize all of these end behaviors. polynomial functions. So a special case of a polynomial function is the power function, which means a polynomial function consists of either 0, so even the 0 is considered a polynomial function, or the sum of a finite number of non-zero terms, each of which is a product of a number called the coefficient of the term and the variable raised to a non-negative integer power. The polynomial function is a function that can be written in the form f of x equals a sub n x to the n power, that is the leading coefficient, times x to the highest power plus, and then you keep adding until you have a polynomial. Sometimes you end up with a constant, which is the last term. Sometimes you don't have that. Here is a simple example. So if I'm going to write f of x equals to negative 3x to the third plus 2x squared minus 1, then this is considered a polynomial. Notice how I always start with the highest power and then the least and then the least, and until I end up with a constant term. So that is considered a polynomial function. And this form is called the general form of the polynomial function, or the general form of the polynomial function. So if we were given a polynomial function, how do you identify the degree and the leading coefficient? In order to identify the degree and the leading coefficient, first you're going to identify the highest power of x to determine the degree of the function. So the degree of the function is the highest power of x in that polynomial. How do we identify the leading term? To identify the leading term contains the highest power of x. So that would be the leading term. So the leading term is the term with the highest power of x. To identify the leading coefficient, basically when you identify the leading term, the leading coefficient is going to be the coefficient of the leading term. So if we have this example right here, we have f of x equals 3 plus 2x squared minus 4x to the third power. We would like to identify the leading coefficient, the degree, and the leading term for this function. So in order to identify the degree, we said the degree, it is the highest power of x. So the highest power is, we have 2 here and we have 3, which means the degree is the 3. Now that we identified the degree of the polynomial, we can identify the leading term, and then from there we can identify the leading coefficient. So in this case, the leading term is the term with the highest power. So here is the term, here is another term, and here is the third term. Notice how the last term has the highest power. You have to take the term with the coefficient and the sign of it. So the leading term is negative 4x to the third power. That is the leading term, which leads us to the leading coefficient is the coefficient of the leading term, which is in this case negative 4. So the leading coefficient is negative 4. Here is another example. F of x equals 2x squared times x minus 4 times x plus 3 all squared. So this is kind of a little bit tricky. In order to identify the degree of the polynomial, notice how all of these are multiplied together. We can basically multiply everything out and find out the leading term, the degree, and the leading coefficient. However, there is an easier way to figure that out. So in order to find the leading term in this case, I'm going to ignore any constants that I see, not the coefficients, but the constant terms like this one and that one right there. So I'm going to rewrite everything without it. So I will have 2x squared times negative x times x raised to the second power, which is, now it's easier to multiply since I eliminated the constants. Now I will end up with the leading term. This is the leading term, which is going to be negative 2x to the 1, 2, 3, 4 to the fourth power. So if you multiply these out, you will end up with negative 2x to the fourth power. Basically what I did, I counted how many x's I have. I have 2 here, 1 here, 2 here. So x to the fourth power. So that is the leading term. Now that I found the leading term, I will be able to determine the degree and the leading coefficient. The degree is going to be the highest degree, which is the degree of the leading term. In this case, it's 4. And then the leading coefficient is the coefficient of the leading term, which is in this case -2. So we found the degree, the leading coefficient, and the leading term for that polynomial. Intercepts and turning points of a polynomial function. Intercepts and turning points of a polynomial function. A turning point on the graph, or a turning point on a graph, is a point at which the graph changes direction from increasing to decreasing or decreasing to increasing. In this specific example of this graph you see here, it's increasing on the segment that I highlighted, and then it turns the behavior at this point, so that is a turning point, and then it turns into decreasing over this interval, and then again it changes at this behavior, so that is also a turning point, and then it turns into increasing one more time. So for this case we have 2 turning points. We have 2 turning points. Now you might be tempted to identify these 3 points as turning points, but they're not. The behavior doesn't change at these points. These are basically x-intercepts. And this is a y-intercept as well. It's very close to the turning point, but it's not a turning point. Why do we look at turning points? Because there is a relation between the degree and the turning points. There is a relation between the degree and a turning points. In the context of polynomials, degree, turning points, and x-intercepts are all related to the behavior and the characteristics of the polynomial function. How is the degree related? The degree of the polynomial is the highest power of the variable. Usually that is the leading term power, the power of the leading term. For example, in the polynomial f of x equals 3x squared minus 2x plus 1, the highest power is 2, so the degree of the polynomial is 2. How is that related to the turning points? So if you notice here, turning points, also known as local extrema, that is a maximum or minimum, are the points where the graph of the polynomial changes direction from increasing to decreasing and vice versa. So if the polynomial has a degree n, it can have at most n minus 1 turning points. So for the previous example, for this example right here, I could say that it has at most 1 turning point because the degree was 2. So that is the relation between the degree and the turning points. And if you were given the turning points, you will be able to determine the degree. So the degree is basically turning points plus 1. Here is an example. So if I said the previous example, the similar one, f of x equals 3x squared minus 2x plus 1, this is a degree 2. It can have at most 1 turning point, and vice versa. If I said a polynomial has at most 1 turning point, I know it's going to have a degree of 2 because the degree is equal to the turning points plus 1, and the turning points is equal to degree minus 1. The x-intercepts, or the zeros, or the roots. We can call them x-intercepts, zeros, or roots. The x-intercepts are the points on the graph where the polynomial crosses and touches the x-axis. So either crosses or touches the x-axis. Also called as the zeros or the roots of the polynomial. The number of x-intercepts a polynomial has is equal to its degree, but it can have fewer if some of the roots are repeated. The x-intercepts a polynomial has is equal to its degree, but it can have fewer if some of the roots are repeated. Here is an example. If you have the polynomial f of x equals x minus 1 times x plus 2 times x minus 3, the x-intercepts are 1, -2, and 3. And the degree of the polynomial is going to be 3 in this case. None of these are repeated, so the degree of the polynomial is going to be a 3rd degree. So let's look at some examples and identify the degree of the polynomial based on the turning points. And we're going to see if the leading coefficient A sub n is positive or negative based on the behavior of the power functions that we studied before. We said if A is positive, then the graph of the function is going to be depending on the degree of the polynomial. If it's even, then both arms of the polynomial are going to go up like that. If it is odd, then the arms are going to be one down, one up, and it's going to be increasing. It's going to be an increasing matter right here. You can see right here it is increasing when the leading coefficient is positive and the power is odd. So same here. So for the first graph right here, we can see two turning points. Here is one turning point and two turning points, which leads me to understand that the degree is going to be 3 equals 3, which is the turning points plus 1. I can also identify the degree by using the x-intercepts in this case because I have them. So the x-intercepts are, as you can see here, 1, 2, 3. So the degree is going to be 3. Since the degree is odd, then I will identify which behavior it is. As you can see here, when you trace the graph is increasing. So it's similar to this pattern right here, which means I know that A is positive because it is increasing. So A is positive. So I'm going to say AN is greater than 0. The number of turning points here are 2. So turning points equals 2. So let me just identify. This is if AN is greater than 0. This is even. This is odd. If A sub n, or the leading coefficient, is less than 1, we're going to have two behaviors. If the degree is even, we're going to have an upside down behavior like that, or both arms are down. If it's odd, we're going to have a decreasing behavior. One arm up, one arm down. Okay, so next graph right here. Let's count how many turning points there are. So I can see here 1, 2, 3, 4 turning points. So turning points equals 4, which means the degree is equal to 5. The degree is equal to 5, and the degree is odd. Now, because the degree is odd, I need to identify whether the leading coefficient is positive or negative. The end behavior looks like this graph, where the graph is decreasing. So the end behavior is decreasing. Here is one up and one down, and then something happens in the middle. So it is decreasing, which means it follows this pattern right here, which leads to me understanding that the leading coefficient is going to be negative. The next graph. Now, I do not have x-intercepts here to identify the degree, so that is not an option. In the previous one, I could have basically counted how many x-intercepts there are. Let me see here. 1, 2, 3, 4, 5, and that is exactly the same as the degree of the polynomial. In this case, I don't have x-intercepts, so I'm going to rely solely only on the turning points. 1, 2, 3, 4 turning points. So the number of turning points is 4, which means the degree is going to be turning points plus 1 equals 5. Turning points plus 1. The degree is odd, so it's either this behavior or that behavior. I noticed that it is actually increasing, so the behavior looks like that, which is this one. And that leads me to say that the leading coefficient is positive in this case. Last but not least, here's the graph. Again, I don't have a lot of x-intercepts to count, so I'm going to rely on the turning points here. So 1, 2, 3 turning points. So turning points 3, which means the degree is going to be 3 plus 1, which is 4, so 4th degree. The degree is even, so it's either this behavior or that behavior. Clearly, both arms are up, so I'm looking at a behavior like this, which means the leading coefficient, an, is greater than 0. So that is how you're going to identify the degree, turning points, and the leading coefficient just by looking at the graph of these polynomial functions.